Coulomb did a series of experiments to understand the electric force between charges, and he observed that the force of attraction or repulsion between charges is directly proportional with the product of the charges and inversely proportional with the separation between them. So you have direct proportionality with the product of the charges and inverse proportionality with the distance squared. Usually, we convert proportionality into a formula by using a constant. This is a constant of proportionality. We call it the electrostatic constant. Okay, and this way we can measure the force of attraction or repulsion between two charges and have a numerical answer. The electrostatic constant K depends on the units that we are using. When we use Newton for force and meter for distance and Coulomb for charge, these are the SI units, then the electrostatic constant is about 9 multiplied by 10 to the power 9 in Newton meter squared per Coulomb squared. Coulomb's law is an experimental law. It is based on experimental observations. It is not derived mathematically. It is based completely on observations. So it is an experimental law, a fundamental law of physics. The direction of the forces, as we can see, it's along the same line connecting the charges. So here we have two positive charges. Like charges repels one the another, so you have repulsive forces. F1, 2, the action of 1 on 2. F2, 1, the action of charge 2 on charge 1. These two forces are equal in magnitude, opposite in direction, and they share the same line of action. The same line that connects the two charges is also the line for this force and for that force. If the charges were not of the same type, like this is negative, this is positive, then the force will be attractive force, as we see here. Again, the magnitude of these two forces are equal and the direction are opposite. If you recall what we learned in physics 1, in Newton's third law, the action-reaction pair of forces, so you understand how these forces are equal. If this is the action, then this may be the reaction, and vice versa. You have the option to name any one of them as action and the other one as the reaction. The magnitudes of these forces can be calculated from Coulomb's law. Q1 Q2 over R squared. That is always the case. Some fundamental quantities in nature, the electron is negatively charged, and the charge is the quantum of charge, as we mentioned earlier, 1.6 by 10 to the minus 19 Coulomb. The mass of the electron is 9.1 multiplied by 10 to the minus 31 kilogram. The proton has the same charge as that of the electron, but it is positive, 1.6 by 10 to the minus 19. Its mass, 1.67 multiplied by 10 to the minus 27 kilo. As always, we use SI units. So for mass, it is the kilogram. For charge, it is the coulomb. The third fundamental particle that we have inside the atom is the neutron. Neutron has about the same mass like the proton, but it is in neutral. It is in neutral. The charge is 0. So if you take 1 coulomb of charge and divide that by the charge carried by 1 proton, 1.6 by 10 to the minus 19, the answer is 6.3 by 10 to the power 18 protons. In plain English, you will need that many of protons, 6.3 by 10 to the power 18, added together, the charge of these protons added together in order to have 1 Coulomb. So from this, we understand that the Coulomb is a big amount of charge. Because of that, in problems, most of the time, you will be dealing with micro Coulomb. Micro means 10 to the minus 6 rather than with Coulomb. Example. The electron and the proton of a hydrogen atom are separated on the average by a distance of 5.3 by 10 to the minus 11 meter. Find the magnitude of the electric force and the gravitational force that each particle exerts on the other, and the ratio of the electric force Fe to the gravitational force Fg. This is a nice example that I always like to present when we about Coulomb's law, so that you appreciate the electric force and you have an idea how powerful is this force compared to gravitational force that we are familiar with from physics 1. So applying Coulomb law, the electric force from Coulomb's law, K, Q1, Q2, Q1 is E, Q2 is E. We don't care about the sign, so we use absolute value. So Q1 and Q2 is just E squared divided by R squared. We substitute here for K and for E and for R, the separation between the proton and the electron. Evaluate. The answer is 8.2 by 10 to the minus 8 in newtons. Now, for the gravitational force, we use Newton's law of gravitation, which we learned in physics 1. So it is G me mp over R squared. This is the universal constant G in SI units. This is the mass of the electron. This is the mass of the proton. Again, this is R squared. Evaluate. It is 3.6 by 10 to the minus 47 in newtons. When you compare the electric force to the gravitational force, it is 2.3 by 10 to the power 39. 10 to the power 39. This tells us how strong is the electric force when you compare it to gravitational force. Because of that, when you solve problems, most of the time, we simply ignore the gravitational force. However, there are other problems which depends on the balance, on the equilibrium between electric and the gravitational force. So we leave that to the problems. But if it's not mentioned explicitly, you may just forget about the gravitational forces and just deal with the electric forces. Object A has a charge of +2 microcoulomb, and object B has a charge of +6 microcoulomb. Which statement is true? You have these three options. Any suggestion? Remember Newton's third law, reaction pair of forces. That should help you to solve this question.
Yeah, I'm trying to think. Oh, it's number 2. Okay.
Yeah, so the forces are equal in magnitude and opposite in direction. Of course, this force is a property of both charges. The force from Coulomb's law, it is a property of both charges. We don't care which is bigger or which is smaller. It's the same force. The force is a property of both charges, not of a single charge. Okay? It depends on the product of these two charges, and it has the same magnitude. Remember? it is the same magnitude, regardless of the magnitude of Q2 compared to the magnitude of Q1. The force is the same force in magnitude, okay? Because the force is Q1 Q2 over R squared. The force is a property of both charges, not of a single charge. Okay. Now, to compare Coulomb's law to Newton's law of gravitation, we see the similarity in the format. Both of them are inverse squared laws. Newton's law depends on intrinsic property of matter, which is mass. Coulomb's law depends on intrinsic property of matter, which is charge. Okay? So wherever there is matter, it has intrinsic properties that built within matter. One of them is mass, the other is charge. Okay? So have this in mind, help us to understand things better and to remember these laws better. As we illustrated from that example, electric force is much stronger than a gravitational force. The other difference, electric force can be attractive or repulsive depending on the identity of the charges, while gravitational force is always attractive.